problem we're going to look at now comes from the 2018 AP Statistics exam. Let's just take a look at it real quickly. An environmental science teacher at high school wants to estimate the proportion of students who recycle plastic bottles. So that's a good thing. You would think that a teacher of environmental science would want to know these kinds of things about their students. Are they having an effect on them? Are they teaching them to take care of the earth in some way? And then, so this person decides, this teacher decides to conduct an experiment or survey, we'll say, an observational study, I should say. This is not an experiment because no treatments imposed here. Each student went into the teacher's office one at a time, so the kid was by themselves with the teacher and answered this question with a yes or a no. Okay, so if you think that might be awkward, so do I, right? All right, but let's keep reading. So this 95% confidence interval for the proportion of all students in high school who respond yes was calculated. And then they asked this very interesting question. How many students were in the sample? So we don't know how many students were actually questioned. All right, so let's write down what our confidence interval looks like. We know it's going to be p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Okay, we know it's a one proportion z interval, one sample here, and we even know what the starting and ending numbers are. So we know, for example, that p hat minus z star times this standard deviation formula we just wrote a moment ago is equal to 0.584 from here. And we know we change it to plus. So if I take the same thing again, we get p hat plus z star times the square root of p hat times 1 minus p hat over n equals 0.816. So notice in both cases, this thing is usually called the margin of error. This is called the margin of error also. It's the same expression. Notice it's being added on this one and subtracted on that one, which means that our p hat must be exactly in the middle of those two numbers. So you have to have that realization here, right? You took p hat, you subtracted a margin of error, you took p hat, you added a margin of error here. So p hat has to be exactly in between this number and this number. Okay, so p hat, to get what's in the middle there, you could just average them, I guess. So we'll do 0.584 plus 0.816 over 2. And if you take that into your calculator here, and then we divide, you get a very nice 0.7. Okay, that's really good actually. First off, the nice simple decimal, but then we could also just plug it into the confidence interval formula. So let's go and do that. So 0.7, right? So our confidence interval is going to look like this: 0.7 plus or minus. We need z star. For z star, for 95%, just remind ourselves how you do that. You draw a normal distribution. You mark off 0.95 in the middle. You shade in this area, and you ask yourself what z star goes here. So a good way to do that in your T84 that is go to second vars. There's a button that says VARS. Above it, it says distributions, DISTR. And if you do inverse second vars or distributions, you go to number 3, inverse norm, and you want to type in the area that's in this tail. Well, that's simply 1 minus 0.95 over 2, or 0.025. So you end up getting here negative 1.96. So we're going to plug into this confidence interval, 1.96, and then we have the square root of 0.7 times 0.3 over n. And we know that this thing equals the confidence interval that was given in the problem, which, in case we forgot, was right here. There it is, little star next to it. 0.584 to 0.816. So 0.584 to 0.816. Okay, so it's just a matter of solving the equation here. I guess I'll take the one with the positive. So we'll go to a new page here. 0.7 plus 1.96 times the square root of 0.7 times 0.3 over n equals 0.816. And then at this point, it's really just an algebra problem. So I'm going to do 0.816 minus 0.7. I will get 0.116 equals this. That 0.7 times 0.3, by the way, is just 0.21, so I'm going to write that in there. And so I'll divide both sides by 1.96. We will get the square root of 0.21 over n is equal to 0.05918. Lots of decimals there. I'm just going to leave it there. I'm going to square both sides. And you'll get the following. You'll get 0.21 over n is equal to 0.0035 and more decimals. And so we know ultimately here that we want to do 0.21 divided by this number to get our answer. We do that, we get that n, you get a decimal here of like 59.95, which means n must have been 60. There's some rounding that went on along the way here, so that's why I'm not getting an exact answer. All right, so that's the answer to part A. Let's go look at part B, which is a very easy question. They just ask us here, given the method used by the environmental science teacher to collect responses, explain how bias might have been present. This is common sense, right? You are a student in your environmental science teacher's class. Your teacher meets with you or go in the teacher's office one at a time, so you're by yourself and you're asked this question directly in front of the teacher. And the teacher says, do you recycle plastic bottles? And this is the person who's an environmental science teacher who cares about the environment and gives you your grade. So I think a lot of people are going to say yes to this, even though maybe that's not what they really do. So that would be the kind of bias you'd have here. So you'd probably be overestimating the true proportion of people who would say yes. Okay. And then this problem had a very clever part C. I'm still not bored of this problem when I think about this clever idea. So the statistics teacher at the school was concerned about bias, obviously for the reasons we discussed. And so they came up with an alternate method for collecting student responses. So 300 kids at random were selected. Each student was given the following instructions. Flip a coin by yourself. Don't tell anybody what happens. If you get heads, then you have to say no to the teacher's question. Now, if you think about that, right? So let's say I go home and I flip a coin and I get heads, then I know when the teacher asks me, do I recycle plastic bottles? I'm going to say no. I'm protected in a sense. As a student, I'm not going to worry about my teacher judging me because my teacher doesn't know if I said no because when I flipped my coin, I got heads, or I said no because I really don't recycle plastic bottles. But the teacher can't tell now if someone says no, whether or not the person really says no, like they mean it, they don't recycle bottles, or if when they went home, they flipped the coin and got heads, and that means they had to say no. Okay, and then if you get tails, then you gotta truthfully. Okay, so question number one there. What is the expected number of students from the 300 sample who were would be required to say no because they got a heads when they flipped the coin? Well, 300 of those students times the probability of heads on a coin is 1/2. So you'd expect 150 of them to say no because they got heads. So these 150 kids said no because of getting heads on the coin. Okay, so then finally, based on the results of the sample, give a point estimate, which is a fancy word for just an estimate, for the proportion of all students at high school who respond yes to the question. So notice here, when everything was said and done, 213 students of the 300 said no. So here's where you have to be a little bit clever. Of these 213 students who said no, 150 of them just said no because they flipped the coin, and the coin made them say no. So what does that mean? It means that you have, let's get this right, 213 no's the teacher got, minus 150 of them that just came because they flipped the coin, which means you have 63 real no's. Let me explain what I mean by real no's. In other words, there were 63 people we would have expected who would have gotten tails, and they would said no to the teacher's question anyway. Okay, so the question now is give a point estimate for the proportion of all students in high school who would respond yes to the question. So you have to remember 150 of them said no because they got heads on the coin. So there, you'd expect about 150 kids to get tails, which means that they would answer honestly. And if they were answering honestly, 63 of them were real no's. So then our p hat, or the proportion of people who would have said yes, if you do 150 people minus the 63 real no's over the 150 people who probably got tails, then you get an estimate of, if we do 150 minus 63, we get 87 out of 150. And so we can divide that, 87 divided by 150, and we get a proportion of around 0.58. So this is actually pretty cool at the end. I mean, they don't ask anything else. That you're done there. If you went back to the original problem, though, you'll notice that our confidence interval, just reminding you, it's right here in the middle, was from 0.584 to 0.816. Our 0.58, our p hat of 0.58 does not fall in there. So we did have a little bit high of an estimate based on our confidence interval. I mean, our p hat from our sample was 0.7. So anyway, that's that. Like I said, I thought this way of trying to fix the bias was very clever. Hope you enjoyed it. Thanks for watching.